Somewhere in the North Atlantic, a patch of ocean the size of a continent is getting colder. Every other sea on Earth is warming. This one is going the other way. Scientists just proved why, and the answer is the thing they feared most. A failing current, a cooling sea, and a warning we can finally read from space. Today we follow the cold water and the dying heartbeat of the ocean. If this grips you, like and subscribe. Now, let's begin. Look at a map of the warming world, and almost every ocean glows the same colour. Warmer, redder. Year after year, the seas soak up the heat we pour into the sky, and the map keeps blushing toward crimson. Then your eye catches something wrong. South of Greenland, below Iceland, a bruise of blue sits in the middle of all that red. One stubborn patch of the North Atlantic that refuses to warm. While the rest of the planet's water heats up, this stretch of sea has been cooling for more than 100 years. Scientists have a plain name for it. They call it the cold blob. It spreads across a region wider than the distance from New York to London, a piece of ocean so large you could drop several countries into it and lose them. And it has been getting colder in the exact century when everything around it got warmer. That is the kind of thing that stops a scientist cold. Heat does not usually skip a spot. When you warm a pot of water on a stove, the whole pot warms. You do not find one corner going icy while the rest boils. So a cooling patch inside a warming ocean is a signal that something powerful is happening under the surface, something strong enough to fight the heat of a warming world and win, at least in this one place. For years, that blue bruise sat on the maps like a riddle. People argued about what made it. Some blamed the winds, some blamed clouds, some blamed short swings in the weather that come and go. And for a long time, the honest answer was that nobody could say for certain what painted that patch of ocean cold. Then, in 2026, a team of researchers went looking with a sharper tool than anyone had used before. They reached past the thin skin of the sea that satellites read, and measured the temperature of the entire column of water, top to bottom, all the way down through the dark, across 70 years of records. And when they laid it all out, the cold reached far deeper than a surface trick of the wind could explain. The chill ran down into the body of the ocean itself. That depth was the clue. Winds ruffle the surface. They do not reach miles down. Whatever was cooling this water lived in the deep, in the slow machinery of the ocean, in the great current that moves water through the Atlantic like blood through a body. The cold blob, they realized, was a symptom, a visible bruise left by a current that is losing its strength. One more discovery turned this curiosity into an alarm. That current is one of the most important systems on the entire planet. It carries heat to Europe. It feeds life across the oceans. It has kept the climate of the North steady for thousands of years. If the cold blob is its bruise, then the bruise is spreading, and it is telling us the body underneath is in trouble. So for thousands of years that assumption held. The current ran, the heat moved, and entire civilizations grew up trusting that the warmth would always arrive. So the first question is the simplest one. What exactly is dying under that patch of blue, and why should a cooling ocean frighten us more than a warming one? Most warnings about a warming planet come dressed in heat, melting ice, burning summers, seas creeping up warm beaches. So when a piece of the ocean turns cold, it feels almost like good news, a small mercy in a feverish world. That feeling is a trap, and understanding why is the key to this whole story. Picture your own body running a fever. Your skin is hot, your face is flushed, and that is uncomfortable, but it is a signal your body understands and can fight. Now picture one of your hands going cold and numb while the rest of you burns. That is a different kind of fear. A cold hand on a hot body carries a darker message. It means blood has stopped reaching that hand. Something in the flow has failed. The cold blob in the Atlantic is that cold hand. The planet as a whole is running its fever, warming almost everywhere. And in the middle of that warming, one patch has gone cold because the warm blood of the ocean has stopped arriving there in the amounts it used to. The chill is a sign of a circulation breaking down, and a broken circulation is far more dangerous than a little extra heat. The difference matters more than it first appears. A warmer ocean is a stronger version of a system we already understand. Storms grow, water expands, coasts flood. Those outcomes are serious, and they follow rules we can predict and plan around. A failing current is something else. It is the machinery itself losing power, the pump that moves heat around the planet beginning to stall. When a pump stalls, you cross into a different world, one that behaves by new rules. And this particular pump touches almost everything. It sets how warm Europe stays through winter. It shapes the rains that feed billions of people. It steers the paths of storms and the height of the sea along entire coastlines. A warming ocean turns the dials on a familiar machine. A weakening current threatens to break the machine itself. There is one more reason a cold patch unsettles scientists more than a hot one. Heat spreads evenly and slowly, and we can watch it climb year by year on a smooth line. The failure of a great current follows a crueler pattern. A current can weaken quietly for decades, holding together, and then reach a hidden edge and come apart quickly. The cold blob is one of the few outward signs we get that this quiet weakening is already underway, a warning light glowing on the surface of the sea. For most of the last century, we could see that light and could not read it. We knew the patch was there. We could not prove what caused it, so we could not be sure how worried to be. A cold spot might have been a passing mood of the weather, here for a decade and gone the next. Or it might have been the first visible symptom of the most important current on Earth losing its grip. Everything turned on which of those was true, and to find out, scientists first had to understand the machine hiding beneath the blue, the vast river of warm water that has kept the North alive for longer than human history. To feel the danger, we have to meet the current itself, time to meet the machine. Under that cold patch runs one of the largest moving things on the planet, and almost nobody outside science knows its name. It is a current, but calling it a current undersells it the way calling the sun a light undersells the sun. Start with a picture you already know. The Gulf Stream. That warm river of seawater that slides up the eastern edge of North America, past Florida, past the Carolinas, out toward the open ocean. Many people have heard of it. What fewer people know is that the Gulf Stream is only the beginning of something much larger. The visible front end of a current that stretches across the entire Atlantic and reaches from the surface down to the black floor of the deep sea. Scientists gave the full system a long and clumsy name, so let's keep it simple and call it the Great Atlantic Overturning. Picture a river with no banks, thousands of miles long, flowing through the middle of the ocean. It carries warm water north along the surface toward Greenland and Europe. Then, in the cold far north, that water sinks into the depths and flows back south along the bottom, a hidden return river running the other way far below the waves, warm water north on top, cold water south underneath, around and around without stopping for as long as anyone can measure. The scale of it is hard to hold in your head. This current moves more water than every river on Earth combined, many times over. Every second, it carries a flow of water so vast that all the Amazons and Mississippis and Niles of the world would look like a trickle beside it. It is a river of rivers, a moving mountain range of water, and it has followed roughly the same path for thousands of years, and it travels as part of something larger. The Atlantic Overturning is one loop in a belt that winds through every ocean on the planet, a single connected ribbon of moving water that scientists picture as a great conveyor. Water that sinks in the North Atlantic can spend centuries creeping along the bottom of the world, sliding past the tip of Africa, into the Indian Ocean, into the Pacific, slowly rising and mixing and beginning the long journey home. One drop can take 1,000 years to make the full trip. The Atlantic piece does the hardest work in that whole global belt. It is the place where the sinking is strongest, where the loop gets its firmest push. Think of the entire planet's ocean circulation as one enormous clock, and the Atlantic Overturning as the mainspring that drives the hands. Weaken the mainspring, and every hand on the clock begins to drag. So this is what hides beneath the cold blob, a river larger than every river on Earth. The mainspring of a machine that reaches into every ocean. A current so steady and so old that entire civilizations grew up assuming it would always be there, the way we assume the ground will stay solid under our feet. And for thousands of years that assumption held. The current ran, the heat moved, the climate stayed within familiar bounds. To understand why it matters that this current is now slowing, we have to see the single most dramatic thing it does for us, the daily miracle that keeps an entire continent warm, Start with a fact that should feel impossible. London sits farther north than almost all of the United States. Draw a straight line east from London and you land in cold Canadian country, in the frozen forest near Hudson Bay, where winters bury the land in snow and the sea locks up with ice. Yet London stays mild. Its people garden through winters that its northern neighbours across the ocean would find unthinkable. Palm trees grow on the coast of Ireland, which sits at the same latitude as the icy heart of Labrador. How can two places on the same line around the globe live in such different worlds? The answer is the current running beneath the cold Blob. That great river of warm water carries tropical heat thousands of miles north and hands it to the air over Europe, like a heater running in the corner of a cold room. The winds pick up that warmth and carry it inland, and an entire continent lives inside the glow. Put a number on it, and the gift becomes clear. Over parts of northern Europe, this current keeps the winters warmer by around 9 to 18 degrees than they would be without it. That is the difference between a chilly afternoon and a killing freeze. It is the difference between farmland and frozen ground. Whole nations built their farms, their cities, and their way of life on the quiet assumption that this warmth would keep arriving. The heat comes from far away. It starts in the tropics, near the equator, where the sun beats down and warms the surface of the sea. The current gathers that warmth and hauls it north, releasing it slowly into the air as it goes. By the time the water reaches the seas around Iceland and Norway, it has given most of its heat to the sky above Europe. The water, now cold and heavy, begins the next stage of its journey. Think of the current as a conveyor belt in a bakery, carrying warm loaves out of the oven of the tropics and setting them down all along the shores of Europe. As long as the belt keeps moving, the warmth keeps coming, loaf after loaf, winter after winter. Slow the belt, and fewer loaves arrive. The room grows colder. That is the danger hidden in the weakening current. A slower belt means less heat delivered to the north, and now the cold Blob starts to make a terrible kind of sense. The patch of cooling ocean sits right in the zone where the current is supposed to be dumping its warmth. A weaker current carries less heat that far north. Less heat means a cooler sea in exactly that spot. The cold Blob is the fingerprint of a bakery belt beginning to slow, the first place where you would expect the missing warmth to show up as a chill. For now, the belt still turns. Europe still gets most of its warmth. The current has weakened, yet it still runs, and the heat still flows, if a little thinner than before. But the cold Blob is proof that the delivery has already started to falter in the one place we would notice first. So the current gives Europe its mild and livable climate. That raises a harder question. What actually drives this enormous belt? What force is strong enough to pull a river of warm water halfway across the world, over and over, for thousands of years? The answer hides in the cold, in the moment the warm water finally sinks. Follow the warm water to the end of its northward journey, and you arrive at the strangest and most important place in the whole system. Somewhere in the cold seas near Greenland and Iceland, the ocean does something that seems to break the rules. It falls. A whole region of surface water plunges straight down into the deep, like water pouring down an invisible drain. This falling is the engine. This is the force that drives the entire belt, and it runs on two simple ingredients that everyone already understands: cold and salt. Start with cold. Warm water is light and floats on top, the way warm air rises to the ceiling of a room. As the current carries tropical water north and the air above Europe steals its heat, the water grows colder and colder. Cold water is heavier than warm water, so by the time it reaches the far north, the water has already become dense and ready to sink. Now add salt, which is the clever part. Seawater is salty, and salt makes water heavier still. As that northern water gives up its heat, some of it also freezes into sea ice. When seawater freezes, the ice squeezes out its salt and leaves it behind in the water below. So the unfrozen water grows saltier and saltier, and saltier water is heavier water. Cold on its own would make the water sink. Cold and extra salt together make it plunge. Picture dropping a stone into a pond. The stone sinks because it is denser than the water around it. In the far North Atlantic, the surface water itself becomes the stone. Chilled and salted until it is heavier than everything beneath it, it sinks in enormous columns, sometimes falling 2 miles straight down into the dark. Across the Northern Ocean, huge volumes of water pour downward like slow, invisible waterfalls hidden inside the sea, and this sinking is what pulls the whole belt along. When that heavy water drops away from the surface, it leaves a gap behind, and something has to rush in to fill it. So more warm water comes flooding up from the south to take its place. The sinking in the north reaches all the way down to the tropics and tugs the warm water forward. The pump works by pulling from the front, hauling the warm current north by the simple act of dropping water out of the way at the far end. That is the secret of the whole machine. A river larger than all the rivers on Earth, and the thing that drives it is water getting cold and heavy and falling. The driver is the plain weight of chilled, salted water sinking in the dark, over and over, dragging the warmth of the tropics behind it. And now you can feel where the danger lives. The entire system depends on that northern water staying heavy enough to sink. Everything hangs on it. If something ever made the water in the north too light to fall, the sinking would slow, the pulling would weaken, and the warm river would lose the very thing that keeps it flowing. There is a force loose in the world right now doing exactly that. Something is pouring into the Northern Ocean, quietly making the water lighter, working against the sinking that holds the whole belt together. It arrives cold and clear and endless, and it may be the single greatest threat this ancient current has ever faced. A heart does two jobs at once. It pushes fresh blood out to every corner of the body, and it pulls the used blood back to be cleaned and refreshed. The Great Atlantic Overturning does the same thing for the world's oceans, and once you see it that way, you understand why scientists lose sleep over its health. The first job is breathing. When that heavy northern water sinks and dives into the deep, it carries the surface with it, and the surface is rich in oxygen, freshly soaked up from the air above. So every time the water plunges in the north, it drags a great gulp of oxygen down into the deep ocean. Without that plunge, the deep sea would slowly suffocate. The sinking is how the bottom of the ocean breathes. The return trip does the opposite and equally vital work. Far to the south, near Antarctica, winds pull that deep water back toward the surface in a slow rising called upwelling. And the water that rises has spent centuries on the ocean floor gathering the remains of everything that ever died and drifted down. It comes up loaded with nutrients, the underwater equivalent of rich soil. Where it surfaces, life explodes. Tiny plants bloom in vast green swirls. Small fish feed on them, bigger fish feed on those, and entire fisheries that feed millions of people rest on that rising nutrient-heavy water. So the current feeds the sea, the sinking carries oxygen down, the rising carries food up. Between them, they keep the whole ocean alive from top to bottom, a single slow heartbeat, pumping breath into the depths and nourishment to the surface. There is a third job, and it may matter most of all. The ocean is the planet's great sponge for carbon, the gas that warms our world. When the northern water sinks, it carries dissolved carbon down with it, locking it away in the deep for centuries where it cannot heat the sky. This current is one of the main ways the planet buries its own heat-trapping gas. Slow the sinking, and the sponge stops soaking. More carbon stays up in the air, and the warming that started the trouble grows worse. The weakening current would feed the very heat that is weakening it. Now hold all three jobs together, and you can see why this is called the beating heart of the oceans. It breathes for the deep. It feeds the surface. It buries the gas that overheats the world. Every one of those jobs runs on the same simple act of cold, heavy water sinking in the north, and that is the frightening beauty of it. A heart fails as a whole. When it weakens, the whole body feels it, every organ starved at once. So it is with this current. Slow the sinking and the harm spreads everywhere the water reaches, which is everywhere. The breathing, the feeding, and the carbon burial all weaken together. For thousands of years that heart has beaten steadily, and the oceans have thrived inside its rhythm. We grew up taking a full sea and a living deep for granted, never knowing that a single slow current was quietly keeping it all going. Now the rhythm is faltering, and the thing making it falter is something ordinary, something clear and cold, melting off the largest island on Earth and slipping quietly into the sea. Meet the thing that is slowing the heart. It is water. Fresh, cold, clean water, and there is more of it pouring into the North Atlantic every year. Greenland is the largest island on Earth, and most of it lies buried under a sheet of ice more than a mile thick in places. That ice holds a staggering amount of frozen fresh water, enough that if all of it melted, the world's seas would rise by more than 20 feet. For thousands of years, that ice sat frozen and still. Now, in a warming world, it melts faster every decade, and the meltwater runs off the island and into the sea in rising floods. Remember what keeps the current alive. The northern water has to stay heavy enough to sink. It stays heavy because it is cold, and above all because it is salty. Salt is the weight that makes it fall, and fresh meltwater carries no salt at all. So picture what happens when all that Greenland melt pours into the Northern Ocean. It spreads across the surface like a thin, fresh lid, watering down the salty sea below. The water grows less salty. Less salty water is lighter water, and lighter water resists sinking. The very fuel that powers the sinking, the saltiness of the Northern Sea, gets diluted year after year by a flood of fresh water that keeps growing. Think of it like trying to sink a swimmer. A person carrying heavy weights drops straight to the bottom of a pool. Strip those weights away, and the same person floats. The meltwater is stripping the weights off the Northern Ocean. Rob the water of its salt, and it loses its ability to fall, and the whole belt loses its pull. And this is a tap nobody can turn off. As long as the world stays warm, Greenland keeps melting, and the fresh water keeps coming. Every warm year adds more melt, and every bit of melt makes the northern water a little lighter and a little less willing to sink. The current has run on salt for thousands of years, and we are slowly washing the salt away. The numbers are hard to picture, so hold on to one image. Greenland now loses hundreds of billions of tons of ice every single year, and much of that ends up as fresh water in exactly the seas where the sinking happens. It is as if someone left a tap running over the one spot in the ocean that can least afford it, and turned the tap wider open every year. For a while, the current can shrug this off. The system is tough, built to handle a certain amount of fresh water. It has weathered wobbles before over its long life. So for years the meltwater pours in, and the current only eases off a little, weakening slowly, gracefully, giving no sign of alarm. Watch that gentle slowing, and you might tell yourself the current is simply adjusting, finding a new and slower balance, handling the stress. Up to a point, that comfort would be right. The trouble is the point, because this gentle, manageable weakening runs out somewhere ahead, at an edge where the slow easing turns into something sudden and violent, and the cold blob may be the first sign that we are drifting toward it. To understand that edge, we first have to see how we caught the current in the act of weakening at all. And the proof came from the strangest place. It came from the cold blob itself. For a long time, scientists faced a maddening problem. The current they most needed to watch runs deep and wide and mostly invisible, buried under miles of ocean. You cannot see a current that flows 2 miles down. You cannot photograph the sinking. So how do you take the pulse of something you cannot see? They found a clever trick. A weakening current leaves a mark on the surface, a pattern in the temperature of the sea that acts like a signature. When the current carries less warm water north, the far north cools in that one telltale patch. Meanwhile, warm water piles up farther south, unable to move along as quickly, so that region runs a little hotter than usual. Cool in the north, warm to the south. That paired pattern is the fingerprint of a slowing current, and a fingerprint can be read from space. Satellites circle the planet measuring the temperature of the sea surface across the whole Atlantic, day after day, year after year. Scientists learned to look for that signature in the satellite maps, the cool patch sitting beside the warm one. When they found it, and watched it deepen over the decades, they had their first real evidence that the current was losing strength. The cold blob was one half of that fingerprint, glowing right where the theory said it should be. For years, that fingerprint was the best clue we had. It let scientists estimate that the current had already weakened noticeably over the last century, dropping to what many believe is its weakest state in more than 1,000 years. That is a startling claim about something you cannot directly see, resting entirely on patterns read from the skin of the sea. The trouble is that the skin of the sea can lie. The surface of the ocean is a busy, restless place, pushed around by winds, stirred by storms, warmed and cooled by the air above. A cool patch on the surface might come from a slowing current, or it might come from a run of windy years, or a shift in the clouds, or some passing mood of the weather that has nothing to do with the deep. Reading the current from the surface alone always carried that doubt. The fingerprint looked convincing, and it might have been a coincidence dressed up as a signal. That doubt gave comfort to anyone who wanted to look away. Every time the cold blob deepened, someone could argue it was just the wind, just a phase, here today and gone in a decade. And for years, nobody could fully rule that out. The signal lived on the surface, where too many other forces could fake it. So the cold blob sat in a strange limbo. It matched the theory perfectly. It appeared exactly where a weakening current would put it, yet it floated on the surface, in reach of a dozen innocent explanations, and a fingerprint on the surface can only tell you so much. What scientists needed was a way to reach past the restless skin of the sea and check whether the cold ran deeper, down where the wind cannot go and the weather cannot fake it. If the chill lived only on the surface, the doubters were right, and the cold blob meant little. If the chill reached far down into the body of the ocean, then the wind was innocent, and something far larger stood accused. In 2026, a team finally reached into the deep to find out. And what they pulled up settled the argument. The team did something nobody had done at this scale before. They chose to ignore the noisy skin of the sea that had fueled years of argument and look instead at the whole body of water beneath it. They gathered temperature readings from top to bottom, from the sunlit surface down through the cold middle layers and into the deep, across a stretch of 70 years of records reaching back to the 1950s. The question they asked was simple. How deep does the cold blob go? If the chill lived only in the top layer, the wind could have made it and the whole thing might mean nothing. If the chill reached far down, past where any storm or breeze can stir, then only the deep machinery of the ocean could be behind it. The answer came back clear and cold. The chill went deep, far below the reach of wind and weather, down in the layers where only the great sinking currents move the water. The cooling was there, plain in the record. This was a cold that lived in the bones of the ocean, in the exact depths where the overturning does its work. No passing weather could reach that far down. Only a change in the current itself could leave a mark so deep. That single finding flipped the cold blob from a suspicious clue into hard evidence. For years, people could wave the cool patch away as a trick of the wind. After this, that escape closed. The cold ran too deep for wind to explain, and it sat exactly where a weakening current would place it, in the very waters the current controls. The fingerprint on the surface finally had a body beneath it, and the body confirmed what the surface had only hinted. The scientists laid it out plainly. The cold blob, they concluded, is a direct sign of the Great Atlantic Current weakening. The patch refuses to warm because the current that used to warm it has grown too weak. The chill and the slowdown are the same event, seen from two angles, and the deep measurements proved the link in a way the surface never could. Put yourself in that moment. For decades, this worry rested mostly on models, theory and readings of the sea surface, always shadowed by the chance the alarm was a coincidence. Now the alarm stood on something solid. Real thermometers, real depths, 70 years of measurements, all pointing the same way. The weakening had stepped out of the models and into the water itself. The researchers spoke without softening it. They called the strong evidence for a weakening current a serious concern for society, and they set it beside a growing pile of other warnings that all point toward the same edge. A current this important, weakening this clearly, is the kind of thing that moves a scientist from careful worry to open alarm, and this is why the title of this story is what it is. For years, the danger was a possibility, a thing the models feared and the surface hinted at. With the deep cold confirmed, the fear became an observation. Scientists spent decades dreading the day they would catch this current weakening in the real world, in hard data, past all doubt. That day arrived, written in the temperature of the deep Atlantic. One study rarely settles a question this large. So while these researchers read the cold in the deep, another team, far to the west, was listening in a different way. And they heard the same thing. A good scientist never trusts a single explanation until the rivals lie dead. And the cold blob had rivals, several honest ideas about what might chill a patch of the Atlantic with no failing current involved. Each had to be beaten before the weakening current could stand alone. The first rival was the meltwater itself, in a simpler role. Fresh water from Greenland is cold. Pour enough cold melt onto the surface, and maybe that alone cools the patch. No deep current required. It sounds neat. It falls apart on the depths. Meltwater floats. It spreads in a thin, chilly film across the very top of the sea. A cooling caused by melt alone would sit in that shallow film near the surface. Yet the chill in the cold blob reaches far down into the deep layers, where surface melt cannot go. The melt cools the skin. Something else cools the body. The second rival was pollution. For much of the last century, factories and ships poured tiny particles into the air, and those particles can shade the sea and cool the water beneath. Maybe the cold blob was just a patch of ocean sitting under a dirtier sky. This idea fails on timing. As nations cleaned their air over recent decades, that shading faded and the patch should have warmed back up. Instead, it held on and even deepened while the skies above it grew cleaner. A cooling from pollution would have lifted as the pollution lifted. This one stayed. The third rival was the most stubborn, a natural rhythm in the ocean itself. The Atlantic breathes in long, slow cycles, decades of slightly warmer water followed by decades of slightly cooler, a natural swing with nothing to do with any long-term weakening. Perhaps the cold blob was just the cool half of one of these swings, due to reverse on its own in time. This was the hardest rival to rule out, and it is exactly the doubt that shadowed the cold blob for years. What finally beat it was the length and depth of the record. A natural swing comes and goes, it warms back up. The cold blob, across 70 years, kept trending colder and reached deeper than a passing swing should, following the pattern a steady weakening would carve rather than a rhythm that rocks back and forth. One by one, the innocent explanations fell. The melt cooled only the skin. The pollution should have faded and clung on instead. The natural swing should have reversed and kept sinking instead. Each rival explained a piece of the cold blob and choked on the rest. Only one idea explained all of it at once: the depth, the timing, the pattern, and the stubborn refusal to warm. A great current losing its strength. This is how science earns its certainty, by killing the comfortable answers first. The frightening explanation wins only when the reassuring ones have all failed. What remained was the answer nobody wanted, the one thing that could account for cold running so deep for so long. So the cold blob became more than a curiosity or a clue. It became a verdict, delivered by a process designed to doubt itself at every step. The Atlantic's great current is weakening, and the cooling sea is the proof. Yet the deep cold was only one witness. Across the ocean, hanging in the water for more than 20 years, a line of instruments had been listening to the current directly, and they were about to back up everything the cold blob had said. Reach across the Atlantic from the coast of Florida toward the coast of Africa, and for more than 20 years a hidden line of instruments has hung in the water, taking the current's pulse directly. Scientists strung them there in the year 2004, a row of anchored sensors reaching from the surface down to the seafloor, spaced across the whole width of the ocean. They call it an array, and it does something the cold blob never could. It measures the current itself, how much water actually moves. The idea is beautiful in its simplicity. The sensors read the temperature, the saltiness, and the pressure of the water at every depth, all the way across. From those readings, scientists calculate how much water the great current carries past that line every second. For more than 20 years, that array has watched the flow without a single break, the longest and clearest record we have ever had of this current strength. Before it existed, we guessed at the current from scattered snapshots. After it, we could finally watch the current breathe. For years, the array's story stayed murky. The current wobbles from month to month and year to year, and short records get lost in that noise. Early on, the flow dipped, then recovered, and honest scientists warned against reading too much into a decade of jitter. The current might be weakening. It might be jumping around. 2 decades was barely long enough to tell. Then, in 2026, a team took a harder look. They gathered readings from moorings along the western edge of the North Atlantic, at several different points up and down the ocean, and asked whether the current was weakening at all of them, or only at one. A slowdown that shows up in a single spot could be a local fluke. A slowdown that shows up everywhere, at point after point along the ocean, is the whole current losing strength. The answer came back the same at every latitude they checked. The current had weakened at all of them steadily over the 2 decades of record. The slowdown ran up and down the western Atlantic, showing up at each mooring in turn exactly the broad, ocean-wide weakening you would expect from a whole system winding down rather than a local hiccup. Now stand back and see what had happened. 2 completely different methods, working from opposite sides of the Atlantic, had reached the same conclusion. One team read the weakening in the deep cold of the sea, in temperature reaching down through 70 years. The other measured it directly in the flow of the water, in the pulse of the current itself over 20 years of instruments. Different tools, different oceans of data. One answer: the current is slowing. When 2 witnesses who never spoke to each other tell the same story, you start to believe it. The cold blob could have been a coincidence. The array could have been too short to trust. Put them together and the coincidences run out. The temperature and the flow agree. The current that keeps the North alive has measurably lost strength, and we now have it caught from 2 directions at once. That agreement is what moved this from a worry to a finding, and it raises the question that decides everything that comes next. The weakening we can measure is one thing. How close that weakening sits to the edge, the point of no return, is a different and far harder question. And the answer turns on a difference most people miss. For most of the time, scientists have worried about this current. The worry lived inside computers. Researchers built models, vast simulations of ocean and air, fed with the physics of a warming world. The models kept giving back the same uneasy answer. Warm the planet, melt the ice, freshen the northern sea, and the great current slows. Push hard enough, and it can even collapse. Those model warnings were easy to shrug off, and plenty of people did. A model is a guess, after all, a world built inside a machine. Skeptics had a simple reply ready for every alarming projection. It is only a model. Real oceans are messier than any simulation. Show us the actual water doing what your computer says, and then we will worry. For decades that challenge stood, because the real-world record was too short and too noisy to answer it. The deep cold and the moorings changed that. Suddenly the real ocean, measured with real thermometers and real sensors, showed the very weakening the models had long predicted. The simulation and the sea had started telling the same story, and when a warning jumps out of a computer and shows up in the actual water, it stops being a guess and becomes a report from the front line. There was a twist in that agreement, and it landed like a stone. When scientists lined up the real measurements against the full spread of models, the water matched the darker simulations. The real ocean was weakening at least as fast as the gloomier models had feared, and in some readings faster. The measurements landed on the worried end of the range. Understand why that stings. Models never agree perfectly. Some run cautious and show the current easing off slowly, barely changing this century. Others run grim and show it sliding toward real trouble within our lifetimes. For years, we could hope the cautious ones were right and treat the grim ones as worst-case scenarios we would probably dodge. The real-world data took that hope away. The actual ocean was behaving like the grim models, the ones we most wanted to be wrong. A lead scientist behind much of this work put it in blunt terms. The pessimistic models, he said, the ones showing a strong weakening, are unfortunately the realistic ones. That is a heavy sentence. It means the future we had filed under unlikely has quietly moved into likely. It means the guardrail we assumed was there. The hope that the current would only ever ease off gently may never have existed. And there is a reason the real weakening may run even worse than the models show. Many of the simulations leave something out, a piece of the puzzle so tricky that modelers often set it aside. The meltwater pouring off Greenland, the very flood loosening the current, is missing from a lot of these models. Add it back in, and the outlook only darkens. The real ocean carries a burden the tidy simulations never counted. So the gap between guess and fact has closed, and it closed in the worst possible direction. The current is weakening in the real world, faster than the hopeful models promised, carrying a fresh water load those models often ignore. The alarm is no longer theoretical, which forces the hardest question of all into the open. If the current is truly sliding toward the darker path, how close is it to the point where sliding turns into falling? To answer that, we have to understand why the gloomiest models frighten scientists so deeply. The grim models say more than that. The current weakens. They say it can break, and some of them put a date on it that lands inside the lives of people alive today. For a long time, the official word was calming. The world's main climate body, weighing all the evidence, judged a full collapse of this current unlikely within this century. That word, unlikely, let everyone breathe. Whatever happened to the current, at least the worst would wait for some distant future, generations away, a problem for our great-grandchildren. The newer work cracked that calm. When scientists search the data for the warning signs a system gives off as it nears a breaking point, the signs were there. And when they used that data to estimate when the current might actually tip, some studies pointed at a window that made people sit up in alarm. Around the middle of this century, not centuries away, decades, within the lifetime of children already born, sit with what a date like that means. A child starting school today could stand in middle age and watch this current fail. The collapse everyone had filed under far future stepped forward into the near future, close enough to touch. Nothing focuses the mind like a deadline, and this was a deadline scientists had spent years hoping they would never have to write down. The estimates come wrapped in uncertainty, and honest scientists say so loudly. The exact timing is fiercely debated. Some studies still point later, some point sooner, and the error bars are wide. A tipping window is a fog bank, not a calendar date. What almost everyone now agrees on, though, is narrower and still chilling. The current is weakening. The freshwater driver is real. The system has an edge it can fall over. The argument is about when, no longer about whether, and here is the part that gives the timeline its teeth. Beyond that edge, the change becomes something you cannot undo. One scientist described the tipping point as the moment when a shutdown basically cannot be stopped anymore. Before the edge, cut the warming, slow the melt, and the current can steady itself and recover. Past the edge, the current takes over its own collapse, and stopping the warming no longer saves it. The system carries itself the rest of the way down, deaf to anything we do. That is why a date on the tipping point matters so much more than a date on ordinary damage. A flooded coast can be defended, a hot summer survived, and next year offers a fresh chance. A current that crosses its point of no return offers no next year. The window to act closes for good, and it may close within the working life of people reading about it now. So the headline that spread carried a hard edge. The scariest version of the future, long treated as an outside chance, had moved to the centre of the table. The measurements matched the dark models. The dark models pointed at mid-century. And the mid-century mark came stamped with the cruelest word in the whole story: irreversible. To grasp why crossing that line changes everything, and why a current cannot simply be nudged back afterward, we have to look closely at what a tipping point truly is. It works by rules our instincts get wrong, and that gap is where the real danger hides. Our instincts tell us that big, slow things fail slowly. A giant oak takes years to die. A great ship takes long minutes to turn. So we expect a giant ocean current to weaken the way it lives, gradually, over centuries, giving us plenty of warning and plenty of time to step aside. That expectation is the most dangerous mistake in this entire story. Some systems hold steady, and hold, absorbing push after push while barely changing, right up until they cross a hidden line. Then they let go all at once. The line has a name. We call it a tipping point, and the Great Atlantic Current has one. To feel how a tipping point works, remember what keeps this current running. The sinking in the north pulls warm, salty water up from the south. That warm, salty water arrives, cools, grows heavy, and sinks in its turn, pulling up still more behind it. Each sinking feeds the next. The current, in a real sense, keeps itself alive. The stronger it runs, the more salt it delivers to the north, and the more salt in the north, the stronger the sinking. A loop that props itself up. A loop like that stays tremendously stable, until the moment it turns traitor. Keep freshening the northern water, keep watering down its salt, and the sinking slowly weakens. A weaker sinking pulls up less salty water from the south. Less salty water in the north means an even weaker sinking next time. The same loop that held the current up for thousands of years begins, past a certain point, to tear it down. Every turn of the wheel makes the next turn worse. That is the trap of a tipping point. On the safe side of the line, the loop fights to keep the current strong, healing small wounds, shrugging off shoves. Cross the line, and the very same loop throws its weight the other way, driving the collapse it once prevented. The system that protected itself for thousands of years turns and destroys itself, and quickly, because a runaway loop feeds on its own speed. This is why a slow giant can fail fast. The slowness we see today is the loop still winning, still holding the current up against the rising flood of fresh water. That slowness fools us into feeling safe. Yet the closer the current creeps to its tipping point, the weaker the loop's grip, until one final push flips it from healer to destroyer. After that flip, the collapse no longer crawls. It races, feeding itself, and the gentle weakening of centuries can give way to a breakdown measured in mere decades. Picture a person leaning back in a chair, tilting it onto two legs. For a while, small muscles hold them balanced, and a gentle push just rocks them back to safety. Lean a touch too far, past the balance point, and those same muscles cannot save them. Gravity takes over and finishes the fall in an instant. The current is leaning back in its chair, and the flood of fresh water is the slow, steady push tilting it toward the point where balance fails. Where that balance point sits, we cannot yet say. We know only that the current is tilting toward it, and that once it passes, no easy pull brings it upright again, which raises the cruelest problem of all. From the outside, a current safely rocking and a current about to fall look almost exactly the same, and that resemblance is a puzzle scientists have wrestled with for years. There is a picture scientists reach for again and again when they talk about tipping points, because it makes the whole strange idea click into place. Imagine a ball resting at the bottom of a valley. Give the ball a gentle push, and it rolls a little way up the slope, slows, and settles back in the middle. Push it harder, and it climbs higher up the side before gravity wins and returns it to the bottom. The valley protects the ball. However hard the shoves, as long as they stay below a certain strength, the ball always comes home to the low point. That valley is the healthy current, running strong, always sliding back to a steady state no matter how the weather shoves it around. Now imagine the fresh water from Greenland as a hand slowly tilting the whole landscape, making the near wall of the valley lower and shallower year after year. The ball still rocks and returns, so nothing looks wrong. But the wall that holds it in is quietly shrinking. Each year, a slightly smaller push is enough to send the ball closer to the rim. Then comes the fatal moment. One ordinary shove, no bigger than 100 shoves the ball survived before, sends it over a wall that has grown too low to hold it. The ball rolls over the top, and here is the cruelty of the picture. On the far side of that hill lies a second valley, a whole other resting place, and the ball rolls down into it and settles there instead. That second valley is the current switched off, weak, sluggish, and just as stable in its own broken way as the healthy state once was. This is what scientists mean when they say the current has two states, a strong running state in the first valley, and a collapsed feeble state in the second. Both are stable. Both are places the system can rest for ages. The tipping point is the hilltop between them, and crossing it drops the current from one world into the other. Now see why coming back is so brutally hard. To roll the ball back into the first valley, undoing the last small push does nothing. You have to shove it all the way back up and over that hill, against the slope, and the collapsed valley has walls of its own, holding the ball down in the wrong place. Even if we cooled the planet, even if we stopped the melt, the ball would sit stubbornly in the broken valley, held there by the same landscape that now works against us. Getting into the collapse takes one small step too many. Getting out takes a climb the world may not be able to make. That is the meaning of the word that haunts this whole story. Once the current settles into its collapsed valley, turning back the warming leaves it stranded, the system finds a new balance in its failed state and holds there, and it can hold there for centuries, a broken current resting just as comfortably in ruin as it once rested in health. So the danger has a precise shape. A ball, a shrinking wall, and a second valley waiting on the far side. We cannot see the wall directly. We cannot measure from the ball alone how much of it is left. And that blind spot leads to the single, most unsettling truth in the science of this current. The reason a weakening we can watch tells us so little about the fall we cannot. Here is the fact that makes this current so hard to judge, and it upends everything our common sense expects. A current settling into a new, slower, stable rhythm and one sliding toward collapse can look exactly the same from outside. The same gentle weakening, the same smooth, slow decline, the same reassuring line on the graph. Think back to the ball in its valley and the shrinking wall we cannot see. From where we stand, we watch the ball rock a little less energetically each year. That is all we observe, a mild, steady slowing. Yet that same mild slowing fits two completely different futures. In one, the wall is still tall, the ball is safe, and the current is simply finding a calmer running state it can hold for ages. In the other, the wall has nearly vanished, and the ball sits one ordinary push from tipping into ruin. The view from outside gives the identical picture in both cases. This is the trap that has haunted the science for years. Weakening is easy to measure. We have the deep cold, we have the moorings. We can say with confidence that the current is losing strength. What all of that leaves hidden is how much room remains before the fall. Strength and nearness to the edge are two different things, and knowing one leaves you blind to the other. One river shows this better than any graph. Watch a river approach a great waterfall, and you might expect the water to churn and warn you as the drop nears. Instead, the opposite happens. Just above the falls, the river often runs its smoothest and calmest, gliding fast and silent toward the edge, giving the least warning at the very moment of greatest danger. A current can behave the same way, easing into its smoothest, quietest decline in the last stretch before it goes over. The calm can be the approach itself, the water at its quietest, exactly where the danger is greatest. That deception is why the soothing official verdicts and the dire warnings could live side by side so long. Both camps stared at the same weakening. One saw a system settling into safety, the other a system drifting toward its edge. Neither could prove the other wrong, because the thing they both measured, raw strength, cannot tell the calm river from the calm river above the falls, and this is what makes the newest work so important and so unsettling. Scientists have been searching all through this confusion for a way to measure something sharper than raw strength, a signal for how close the current sits to its edge rather than how strong it runs today. A way, in the language of the valley, to measure the height of the wall itself. They have begun to find it. New warning signs, drawn from the deep patterns and long records, give the first real hints of how much margin the current has left. And the early readings from those tools point in a grim direction, toward a wall worn thinner than we would like, a ball closer to the rim than any of us would choose. Before we follow scientists into that way of seeing, we must settle the question that decides how seriously to take all of it. Is a full collapse even truly possible? Could this current really tumble off a cliff, or does it belong to the gentler family of systems that weaken forever and never quite break? The answer waits in the planet's own past, in a time the ice still remembers. To know whether this current can truly fall off a cliff, we need no model and no guess. We need only look back because the Earth has run this exact experiment before, and it left the results written in the ice and the mud. Rewind almost 13,000 years. The planet was climbing out of its last great ice age, warming, thawing, with the huge ice sheets that once buried the North melting back. Across what is now Canada sat a lake unlike anything today, a vast body of meltwater trapped behind a wall of ice, holding more water than all the Great Lakes combined. It was a flood waiting to happen, penned in by a crumbling dam of ice. Then, the dam broke. In one of the largest freshwater releases the planet has ever seen, that titanic lake burst loose and poured into the North Atlantic, dumping a staggering flood of fresh, unsalted water straight onto the very region where the current does its sinking. It was the same wound we are inflicting slowly today, delivered all at once. The salt in the north drowned under a sudden ocean of fresh water, and the water grew too light to sink. The current did what the physics says it must. Robbed of the sinking that drives it, the current crashed. The great belt of warmth to the north faltered and largely shut down, and the heat it had been carrying to the top of the world stopped arriving. Scientists call the cold age that followed the Younger Dryas, and it is the clearest proof we possess that this current owns a cliff and can be pushed straight over it. What makes this precedent so precious and so chilling is how exactly it matches the mechanism worrying us now. The cause then was a flood of fresh meltwater into the North Atlantic. The cause now is a flood of fresh meltwater into the North Atlantic. Different source, larger and faster back then, the same poison poured into the same wound. The planet has already shown us in its own history that this specific machine can be broken by this specific act. The cliff is real, and we stand on its rim. Be careful about what the ancient flood does and does not prove. It carries no promise that our current will collapse tomorrow, or on any fixed schedule. The world back then was a different place, awash in far more ice, with far more water ready to dump into the sea all at once. Anyone who claims the old collapse maps perfectly onto our moment is overselling a frightening story. The past rarely repeats in tidy detail. What the ancient collapse proves is smaller and far more solid. It proves the cliff is real. It proves this current can be shoved past a point of no return by fresh water, flooding the North Atlantic. And it proves that when the current goes, it falls. The Younger Dryas is the planet's own warning label, scratched into ice cores and ocean mud, telling us in plain terms that this current can break, and that when it breaks hard. That leaves the question that decides everything. When this current collapsed in the deep past, how fast did the world actually change around it? Slowly enough to adjust, over long comfortable centuries, or fast enough to upend a human life inside a single lifetime? The answer, buried in the ice, is the most sobering part of the whole story. The ice remembers, and the ice keeps time. Deep in the Greenland ice sheet, snow that fell thousands of years ago lies packed into layers, one for every year, like rings in a tree stretching back through the ages. Drill down and pull up a core of that ancient ice, and you hold a frozen diary of the planet's weather year by year, reaching back across the whole story of the last collapse. Scientists learn to read the temperature of each ancient year from the ice itself, and when they read the years around the Great Shutdown, what they found stopped them cold. The change came at the speed of a turning season. When the current collapsed and the Younger Dryas cold slammed down, the temperature over the North Atlantic region plunged by many degrees in the span of a single decade. Some records suggest big swings arriving in just a few years. A person could have watched their world grow measurably colder within their own lifetime, watched the growing seasons shorten and the winters lengthen, and known that something had gone deeply wrong with the sky. Sit with how strange that is. We picture the ice ages as slow, grinding things, glaciers creeping across continents over tens of thousands of years. Yet here, buried in the ice, is proof that the climate can also lurch. It can hold steady for centuries and then jump to a new setting in the time it takes a child to grow up. The collapse of the current was one of those lurches, maybe the sharpest the ice remembers, a whole hemisphere yanked into a colder world almost overnight in the long story of the Earth. And when the cold finally ended, it ended just as violently. After more than 1,000 years locked in the deep freeze, the current switched back on, and the warmth came flooding north again. The ice cores show the temperature leaping back up, once more in the space of a decade or so. In both directions, the climate snapped from one state to the other, like a switch thrown hard, first off then on. This is the piece that turns the ancient collapse from a history lesson into a warning that grips the throat. The real terror lives in the speed at which failing rewrites the world above it. A slow decline over 1,000 years we could perhaps prepare for, adapting a little each generation. A hemisphere flipping to a new climate inside a single decade is a different kind of threat entirely. Faster than farms can move, faster than cities can adjust, faster than a society can plan. The ice tells us plainly what this current is capable of. When it goes, it can drag the climate of half the planet down with it in years, not ages. The warmth that took thousands of years to build can vanish in the length of a childhood. That raises the obvious and urgent question. If the Earth has done this before and done it so fast, are we simply reliving the same story, heading for the same violent flip? Or is our world different enough that the ancient collapse tells us less than it seems? The answer is a mix of comfort and fresh alarm, and both halves matter. Start with the comfort because it is real. Our world today differs sharply from the world that collapsed almost 13,000 years ago, and the differences matter. Back then, the planet was buried in far more ice. Colossal sheets still lay across North America and Northern Europe, leftovers from the Ice Age, holding oceans of frozen water ready to pour into the sea. The lake that broke and flooded the North Atlantic was a monster with no equal today, and there is simply no reservoir of meltwater on our continents now that could dump so much fresh water so suddenly. The single greatest trigger of the ancient collapse, that one titanic flood, cannot repeat, because the giant lakes that fed it are long gone. So the crudest version of the nightmare, an overnight flood shutting the current off in a year, fails to fit our moment. Greenland is melting, and melting fast, yet it releases its water gradually over decades rather than in one catastrophic burst. In that sense, we are pushing the current more gently than the ancient world did. The shove is softer and slower. Hold on to that comfort and then let it go, because the differences cut both ways and the other side is grim. The ancient collapse happened in a world that was otherwise cooling or holding steady, a planet settling out of its ice age. We are pushing the current in a world we are heating harder and faster than the Earth has warmed in a very long time. The freshwater flood from Greenland is only one of our shoves. We are also warming the surface of the Northern Ocean directly, and warm water, like fresh water, is lighter and less willing to sink. So we attack the current from two sides at once, freshening it and heating it together, weakening the sinking by both roads. The ancient world pushed with one hand, we push with two. There is a deeper difference, and it is the most sobering of all. The ancient trigger was a single event. The flood came, the current fell, and then the flood was spent, its lake emptied into the sea. Our push has no such ending. As long as we keep warming the planet, Greenland keeps melting and the Northern Ocean keeps heating year after year after year. Instead of delivering one great shove and stepping back, we lean on the current continuously, harder every decade with no lake that will ever run dry. The pressure we apply keeps climbing for as long as the warming continues, so the two situations rhyme without matching. The ancient world hit the current with a single massive blow and watched it fall. We are pressing on it with a slower, steadier, endless force, from two directions instead of one, in a world growing warmer rather than colder. Their collapse proves the current can break. Ours may be building toward the same edge by a longer and stranger road. The honest summary is a hard one to sit with. We probably cannot trigger the exact ancient collapse, the overnight flood, in our world. What we can do is something the ancient world never attempted. Push the current toward its edge slowly and relentlessly, with warming and melting combined, and refuse to stop pushing. Whether that gentler, endless pressure can topple the giant is the very question scientists are racing to answer. And to answer it, they had to solve a problem we have already glimpsed. They were reading the wrong dial. For years, scientists watched this current the way a driver watches a speedometer. The moorings across the Atlantic, the deep temperature records, the satellite fingerprints, all of them measure one thing above all: speed. How much water the current moves, how strong the flow runs today. And a speedometer is a fine tool for one job, telling you how fast you're going right now. There is a question a speedometer cannot answer, and it is the only question that matters here. How far until you run out? Picture driving across a desert at night. Your speedometer reads a steady, healthy 60. Everything feels fine. But somewhere on your dashboard sits a second gauge, the fuel gauge, and it is the one that decides whether you reach the far side or die stranded in the sand. A car cruising along at full speed can be 1 mile from an empty tank. The speed tells you nothing about the fuel. This is the trap the whole science fell into. We built better and better speedometers for the current, and we read them carefully, and they told us the current was slowing. Useful, frightening, real. Yet the slowing speed could never tell us the thing we most needed to know. How much fuel is left in the tank? How close the current sits to the point where it sputters and dies? A current running at half strength might be perfectly stable, cruising along its new, slower speed for centuries, or it might be a hair away from empty. The speed alone cannot separate those two futures. Remember the ball in its shrinking valley. The speed of the current is how hard the ball happens to be rocking on any given day. The fuel is the height of the wall still holding it in. You can watch the rocking all you like. It will never show you how much wall remains. A ball can rock gently inside a tall, safe wall, or rock just as gently beside a wall worn down to nothing. The motion looks the same. The danger could not be more different. And here is why this haunted the field for so long. Every argument about when the current might collapse was, underneath, an argument between people staring at a speedometer and trying to guess the fuel. The cautious voices looked at the steady speed and said, "Plenty of tank left, no collapse this century." The alarmed voices looked at the same speed and feared the tank was nearly dry. Neither side could win because the tool they shared, raw speed, simply does not measure fuel. They were reading the wrong dial and arguing about the wrong number. What the science desperately needed was a fuel gauge, some way to measure, from the outside, how much margin the current had left before its edge. A signal that changes as the wall gets lower, that warns you the tank is emptying even while the car still cruises. For a long time, no such gauge existed, and the fog stayed thick. Then, in the last few years, scientists found one. They discovered that a system creeping toward its tipping point gives off a subtle signal, a change in its very behaviour that has nothing to do with its raw strength. A way, at last, to read the fuel instead of the speed. And when they built that gauge and pointed it at the Great Atlantic Current, the needle told a story that raw speed had been hiding all along. The fuel gauge scientists found is one of the most beautiful ideas in all of climate science, and it rests on a simple truth about anything nearing a breaking point. Things that are about to tip lose their bounce. Think of a healthy person shoved off balance. They stumble, catch themselves, and snap back upright in an instant. Their body is resilient. Now think of someone frail and exhausted given the same shove. They wobble, sway, take much longer to steady themselves, and barely recover before the next push. The recovery has gone slow and shaky. That sluggish, unsteady bounce back is the sign of a system running low on strength, and it shows up long before the final fall. Scientists realized that a current approaching its tipping point should behave the exact same way. A strong, healthy current, knocked off balance by a stormy year or a warm spell, should shrug off the disturbance and return quickly to its normal rhythm. A current creeping toward its edge should recover more and more slowly from each knock, wobbling longer, taking its time to settle, growing twitchy and unsteady. The system loses its bounce, and crucially, this loss of bounce can appear while the current still runs at decent strength. It is a change in behaviour, in resilience, that the raw speed completely hides, a true fuel gauge. So scientists went hunting for that loss of bounce in the long records of the Atlantic. They studied how the cold blob and the surrounding sea wobbled and recovered over more than a century of data, searching for the telltale signs of a system growing frail. They measured how jumpy the current's behaviour had become, and how sluggishly it returned to normal after each natural disturbance. The needle moved in the wrong direction. The records showed the current losing its resilience over the decades, its recovery growing slower, its wobbles growing longer and larger, exactly the pattern a system shows as it drifts toward a tipping point. In the language of the fuel gauge, the tank was reading low. In the language of the ball in the valley, the wall was measurably shrinking. The current was doing more than slowing. It was losing the very stability that keeps it in the healthy state at all. This was the finding that turned a distant worry into a countdown. For the first time, scientists had a tool that spoke to the real question, and its answer was grim. The current has grown weaker, and worse, less stable, closer to its edge, running lower on the reserve of resilience that stands between the healthy world and the collapsed one. Honesty demands a caveat, and scientists give it freely. Reading these warning signs from old, imperfect ocean records is hard, delicate work, and the exact readings carry real uncertainty. Different teams, studying the signals in different ways, come up with different estimates of how much fuel is left. The gauge exists now, which is a genuine breakthrough, yet it is a rough gauge, its needle blurry, easier to read as a direction than as a precise number. What almost no one disputes is the direction. Whichever way you read the new signals, they point the same way, toward less stability, toward the edge, toward a current with less margin than we once hoped. And that shared direction forced the field into a fierce and unresolved argument. If the tank is emptying, exactly how much is left? Even with the new fuel gauge, our clearest forecasts still come from the great climate models, those vast simulations of ocean and air. And there is a quiet, uncomfortable truth about those models that every honest scientist will admit. They are probably too optimistic, and the reason is baked into how they are built. The very way they work pushes them to underplay the danger. Consider the size of the problem. The world's oceans are enormous, and a computer can only chop them into so many pieces. To simulate the whole planet, modelers carve the ocean into a grid of boxes, and each box is often around 60 miles across. Anything smaller than a box the model cannot truly see. It smears the small stuff into an average. And here is the trouble. The places where the current does its sinking, those crucial spots in the far north where water plunges into the deep, are often small, sometimes far smaller than a single box. The most important action in the entire system happens at a scale the models can barely resolve. They paint the sinking in broad, blurry strokes when the real thing is fine and sharp. A machine that blurs the most delicate part of a system tends to make that part look sturdier than it is. Sharp edges are where things break. Smooth over the sharp edges, and the model shows you a current that bends gracefully when the real one might snap. So the built-in blurriness of the models likely nudges them toward the calmer, more reassuring answer, hiding the very fragility the new warning signs are picking up. There is a second miss, and it may be the larger one. The models have kept being surprised by the real world in one specific way. They keep underestimating how fast the ice melts. Time and again over recent decades, the great ice sheets have lost their frozen mass faster than the models predicted, shedding water into the sea ahead of schedule decade after decade. Real ice keeps outrunning the simulations of ice, and more meltwater, arriving sooner than expected, means more fresh water freshening the northern sea, more push against the sinking sooner than the models assume. Stack those two misses together and the picture darkens. The models blur the fragile sinking zones, making the current look tougher than it is, and they lowball the flood of meltwater, making the attack on the current look weaker than it is. Both errors lean the same way, toward comfort, toward a gentler forecast than reality is likely to deliver. When a set of tools tilts toward good news, and those same tools still forecast trouble, the real trouble is probably worse than the tools admit. This is why so many of the scientists closest to this current now say the same unsettling thing. The official projections, the ones drawn mostly from these models, may be the best case rather than the middle case. The likeliest future could sit gloomier than the average model suggests, because the average model is built to miss exactly the features that would make it gloomier. This shifts the odds, rather than proving collapse is near. It says our most trusted forecasts carry a thumb on the scale toward calm, and we should read their reassurances with that thumb in mind. The current may have less time than the tidy simulations promise, and that suspicion, that reality is outrunning the models, sits at the heart of the sharpest disagreement in the whole field. Fairness demands that we stop and hear the other side, because a real scientific argument is happening here, and the calmer voices are serious researchers with serious reasons. Plenty of experts look at the same evidence and reach a far more reassuring conclusion, and they deserve a fair hearing. Their case starts with the models we just criticised, which they defend. A blurry model, they argue, is still our best physics, still built on the real laws of the ocean, still tested against reality countless times, and most of these models, run forward through this century and beyond, show the current weakening substantially yet holding together. It bends, it slows, it stays whole. In the majority of simulations, even under heavy warming, the great current survives past the year 2100, wounded but alive. When most of your best tools agree the current keeps running for a long time yet, these scientists say you should take that agreement seriously. They add a sharp point about the early warning signals, the fuel gauge. Those signals, they caution, get read from old, patchy, second-hand records, from surface temperatures standing in for a current we could not measure directly until recently. A fuel gauge built from such rough materials might give a false reading. The signs of lost resilience could be partly an illusion, an artifact of imperfect data rather than a true emptying of the tank. Extraordinary claims, they insist, need cleaner evidence than a century of stitched-together sea surface temperatures. Some of the most recent work backs this cautious view. A study modelling the actual meltwater pouring off Greenland, feeding realistic floods of fresh water into a detailed simulation, found the current weakening through the coming centuries and still refusing to fully collapse, holding on even to the year 2300. In that view, the current is remarkably tough. Push it hard, freshen it, warm it, and it sags without shattering, a giant that bends much further than the alarmists fear before it ever risks breaking. The Karma camp also makes a point about history that deserves respect. The ancient collapse, they remind us, needed a truly colossal flood, a monster far beyond anything Greenland can deliver today. If it took that much fresh water to break the current back then, perhaps the gentler push we apply now, however relentless, simply lacks the strength to topple it. The giant may groan and lean for centuries without ever going over. Take this side seriously, because the science is genuinely unsettled, and pretending otherwise would be its own kind of dishonesty. A weakening current is close to certain, measured from two directions and hard to deny. A full collapse within our lifetimes remains contested, defended by careful people on the Karma side who may turn out to be right. The honest state of the field is a real disagreement, with the verdict of doom far from settled. Yet even the Karma voices agree on the parts that should worry us. They agree the current is weakening, and weakening clearly. They agree a collapse is physically possible if we push hard enough for long enough. They agree the stakes, should it happen, would be enormous. Their comfort is about timing and threshold, about how hard the giant is to topple, and leaves untouched the question of whether the danger is real. So the argument has moved past whether the current is in trouble. It is about how deep the trouble runs, and how soon. And that narrower question turns out to be maddeningly hard to pin down. So why can brilliant people, staring at the same ocean, land so far apart on the single question of when? The disagreement is a mark of how brutally hard the question is, and understanding why is strangely clarifying. Start with the shortness of our clear vision. We have truly watched this current, measured it directly and continuously, for only about 20 years. 20 years is a blink in the life of a system that moves on the rhythm of centuries. Imagine trying to judge the health of a 100-year-old forest by watching it for a single afternoon. You might catch a falling branch and cry disaster, or a moment of calm and declare all is well, and both readings would be nearly worthless against the vast slow life of the trees. Our direct record of the current is that single afternoon. Everything older comes from clues and stand-ins, from ice and mud and sea surface temperatures, each one blurrier than a real measurement. Then there is the nature of a tipping point, which hides the finish line by design. Right up until the moment it tips, a system near its edge can look almost identical to a system that is merely weakening safely. The clearest proof that the current has passed its point of no return would be the collapse itself, arriving too late to serve as any kind of warning. Scientists are trying to spot a line that reveals itself only after it has been crossed. That is why their estimates scatter. They are reading faint early hints of an edge, whose exact location stays hidden until the fall. The methods themselves pull in different directions. One approach studies the warning signals, the loss of bounce, and lands on frighteningly soon, pointing toward the middle of this century. Another approach trusts the big physical models, which mostly hold off collapse for centuries. A third leans on the ancient record and argues about how well the deep past maps onto now. Each method is reasonable, each rests on different assumptions, and because the assumptions differ, the answers differ, sometimes by hundreds of years. The spread in the estimates is really a spread in which clues you trust most. There is also the simple fact that the current is being pushed by our own future choices, which nobody can predict. How fast the current nears its edge depends on how much more we warm the planet, how fast Greenland melts, how much fresh water floods the north in the decades ahead. Those depend on human decisions not yet made. A scientist forecasting collapse is also, quietly, forecasting our behaviour, and our behaviour is the least predictable variable of all. Stack all of this together, and the disagreement stops looking like confusion and starts looking like honesty. The timing is genuinely uncertain because the question is genuinely hard, wrapped in short records, hidden thresholds, competing methods, and an unknowable human future. Anyone who gives you a confident single year for the collapse is selling more certainty than the science can honestly provide. Yet uncertainty about timing is a thin and treacherous comfort, and it is here that many people take a wrong turn. They hear the scientists arguing about when, notice there is no agreed date, and quietly conclude that the whole thing must be overblown. That conclusion is a trap, and it may be the most dangerous mistake in this entire story. because even the gentler outcome, the one the calmer scientists describe, is far worse than most people imagine. Forget collapse for a moment. Set aside the cliff, the tipping point, the switch thrown to off. Imagine only the mildest version of the future that nearly every scientist, calm or alarmed, already agrees is coming. A current that keeps weakening, sliding to a fraction of its old strength, and simply stays there, sluggish and slow, without ever fully shutting down. No collapse. Just a great current running at half power. Even that gentle future would reshape the world. The reason is simple. This current causes harm by slowing long before it ever stops. Every job it does, warming the north, feeding the sea, steadying the rains, burying carbon, weakens smoothly as the current weakens. A current at half strength does its jobs at something like half strength, and the world built around the full strength version feels every bit of the difference. The damage arrives in proportion, growing worse with every notch of slowing, without waiting for any final collapse. And the slowing has already begun. Think of it like a heart that keeps beating, but grows steadily weaker. The person survives simply losing their vigour, tiring on the stairs they once climbed easily, going cold in the fingers and toes, their whole body running a little starved. A weakening current does that to the systems that depend on it. Slowly, unevenly, it starves the edges of the world it once nourished, and a starved world, while it lasts far longer than a dead one, is a harder place to live. Here is the part that makes the partial slowdown so important. It is almost certainly the future we are already living into. The full collapse remains debated, possible, feared, yet uncertain. The partial slowdown is happening now, measured, confirmed, and set to deepen for decades no matter what else occurs. Even if we cut every risk and the current never tips, the weakening already underway will keep grinding forward, dealing out its proportional damage year by year. The mildest scenario is the baseline, the floor beneath all the worst possibilities rather than a hopeful maybe. And the reach of it is staggering, because this current touches so much. A partial slowdown presses everywhere at once, on Europe's weather, on the rains that feed billions in distant lands, on the sea levels lapping at coastal cities, on the fish that fill the nets of entire nations. One weakening current and a dozen distant systems all sag together, each in proportion to the slowing. The harm spreads out along every path the current ever travelled, so the true stakes are wider than the dramatic question of collapse. Even the boring answer, the one where the giant merely sags rather than falls, delivers a slow, spreading global harm that we have already started to feel. The collapse is the nightmare, the slowdown is the near certainty, and the slowdown alone is enough to redraw the maps of where crops grow, where storms strike, and where the sea reclaims the land. To feel what any of this means, we have to leave the abstract talk of strength and stability behind, and walk into the specific worlds this current holds up. We have to see the places that would change and the people who would feel it, starting with the continent that owes this current its very mildness. Europe learned long ago to live inside the warmth. Europe is about to learn what its absence feels like. Europe is a warm lie told by the ocean. The continent sits far to the north, up in the latitudes of ice and long winters, and it stays mild only because the current keeps hauling tropical heat to its shores. Take away that heat, and Europe snaps back to the cold country its latitude says it should be. That snapping back is the nightmare. Picture the winters first. As the current weakens and delivers less warmth, northern Europe would cool, its winters growing longer, darker, and far more bitter. The models that explore a serious slowdown paint parts of the continent plunging into cold that today's Europeans would find shocking, winters with a savagery the region has not known in the whole span of its written history. Cities built for mild, damp seasons would face deep freezes they were never designed to survive. The warmth people assumed was simply the nature of their home would peel away, revealing the harsh northern latitude underneath. The cold is only the opening blow. When you chill one region while the rest of the planet keeps warming, you carve a sharp new contrast between hot and cold air, and sharp contrasts breed violent weather. A colder North Atlantic beside a warmer world would likely whip up fiercer storms, driving them harder and more often into the coasts of Europe. Winds, floods, and battering seas would arrive with new strength, hammering shores that once sat in relative calm. The mild, forgiving climate would give way to something wilder and crueler, Then comes the deepest wound of all, the one that reaches the dinner table. Europe feeds itself on the strength of a long, gentle growing season, warm enough for wheat and every staple crop across vast farmlands. Shorten and chill that season, and the harvests falter. Fields that reliably fed millions could turn marginal, their yields shrinking, their crops failing in the cold and the shortened summers. A continent that has taken its full granaries for granted for centuries would watch its own farmland turn against it, unable to grow what it always grew. Hunger, in places that forgot the meaning of the word, would return to the conversation. Layer these together and imagine a Europe transformed within a lifetime. Winters of a ferocity out of the deep past, storms lashing the coasts with fresh violence, harvests thinning year by year across the breadbasket of the continent, and all of it striking a crowded modern civilization that built its cities, its farms, its entire way of living on the quiet promise that the warmth would always arrive. The promise would break, and hundreds of millions of people would live inside the breaking. The cruelest irony sits at the centre of it. In a warming age gripped by fears of scorching summers and burning skies, one of the gravest dangers is a great and sudden cold, delivered to a wealthy, densely peopled corner of the planet by the failure of a current most of its residents have never heard of. The story everyone expected was fire. The story hiding in the ocean is frost, and Europe, for all its exposure, might escape lighter than the places that never got a warning at all. The failure of this current would reach far beyond the cold shores of the North Atlantic. It would reach into the tropics, into the great rain belts that decide whether crops live or die for billions of people. The continent that owes the current its mildness would suffer. The lands that owe it their rain might suffer more. Follow the current's failure south, all the way to the warm middle of the planet, and you reach the place where it might do its worst harm of all. The tropics, the band of heavy rains that circles the Earth near the equator and decides, each year, whether the crops of half the world will live or die. That rain belt sits where it does for a reason tied straight to this current. By hauling heat into the northern half of the planet, the Great Atlantic overturning helps pull the tropical rains slightly north, settling them over the lands and seasons that billions of farmers depend on. The timing of the great monsoons, the arrival of the rains that feed South Asia, West Africa and beyond, all lean on the balance of heat between the hemispheres that this current helps to set. Weaken the current, cool the north, and that balance tips. The rain belt lurches south, away from the fields that have counted on it for thousands of years. For the people in its path, a lurching rain belt is a matter of survival. Across a broad stretch of Africa just south of the Sahara, farming lives and dies by the summer monsoon. Studies of a weakened current show those rains failing, the season turning dry, the crops withering in the fields. The same models show the mighty monsoon of South Asia, the rains that well over 1 billion people rely on to grow their food, faltering and growing unreliable. Rains that arrive late, or thin, or not at all, in the lands that can least withstand their loss. Sit with the arithmetic of that, because it dwarfs everything else in this story. The cold winters of Europe would strike millions. The failure of the tropical rains would strike billions. Whole regions where hundreds of millions of people already live close to the edge of enough food, push toward drought and failed harvests at the same time, in the same few decades. This is the kind of disruption that uproots populations, empties farmland, and sends people moving in numbers the modern world has never had to absorb. And the deepest injustice sits right here. The people in the path of the failing rains did the least to cause any of it. They burned the least fuel, poured the least warmth into the sky, and drew the least benefit from the machines that are pushing the current toward its edge. Yet a shift in a current thousands of miles away, driven by choices made in distant wealthy nations, could dry out their fields and starve their harvests. The suffering would fall heaviest on those who had the smallest hand in the cause. This is the part of the story that turns a fascinating piece of ocean science into a matter of raw human stakes. A patch of the North Atlantic cools, a current halfway around the world slows, and because the whole climate is one connected machine, the rains fail over a continent, and 1 billion people find their food in doubt. Distance offers no protection. The threads run everywhere. The tropics would burn dry, Europe would freeze, and between those two extremes along the crowded edges of every ocean, A third consequence would rise quietly out of the sea itself, lapping at the doorsteps of the great coastal cities. The same failing current that chills the air and shifts the rain also shapes the height of the sea, and on one particular coastline it is already lifting the water. Cross back over the Atlantic to the eastern coast of the United States, and the failing current leaves a mark that is already measurable, already lifting the sea against some of the most crowded shorelines in the world. This mark has already begun to show. The link is a piece of physics that surprises almost everyone. A strong, fast current does more than carry water forward. It also holds water away from certain coasts, piling the sea up on one side and pulling it down on the other, shaped by the spin of the planet and the force of the moving flow. Along the eastern seaboard of North America, the powerful current has long kept the coastal sea somewhat lower than it would otherwise sit, holding a mass of water offshore. When the current weakens, its grip loosens. That held back water sloshes toward the shore, and the sea along the coast rises, over and above the general rise already coming from melting ice and warming seas worldwide. So the coast from New York up through New England carries a double burden. It faces the same climbing seas as everywhere else on a warming planet, and on top of that, a local bonus rise delivered specifically by the weakening of this current. Scientists have already tied unusually fast stretches of sea level rise along that coast to wobbles in the current, brief slowdowns that let the offshore water surge landward. A short weakening produced a measurable jump in the sea. A long, deep weakening would produce far more. Picture what that means for the cities strung along that shore. Some of the largest, wealthiest, most densely built coastal areas on the planet sight on that stretch of coast. Their streets and subways and airports laid out at the water's edge, planned around a sea that stays roughly where it has always been. Add an extra measure of rise delivered by the failing current on top of the global climb, and the math of every seawall, every storm drain, every flood plan tilts toward failure. High tides reach farther. Storm surges ride in on a higher baseline and strike deeper inland. The ordinary flood becomes the severe one. The quiet cruelty of this consequence is its head start. The cold winters, the failing monsoons, those still lie mostly ahead, waiting on a deeper weakening. The extra sea rise on this coast is here now, already folded into the water lapping at these cities, already nudging the floods a little higher each year. Of all the current's distant effects, this is the one that has most clearly stepped out of the models and into the streets. And it compounds. The more the current weakens in the decades ahead, the more of that held back water comes ashore, and the faster this particular coast sinks beneath the rising sea relative to the rest of the world. A coastline already among the most exposed on Earth would find the ocean climbing against it faster than almost anywhere else, driven by a current failing far out in the deep Atlantic. So the reach of this one current stretches from frozen European winters to dry tropical fields to flooded American streets, three utterly different disasters flowing from a single failing flow. Yet all of them still count the cost in weather and water and food. There is one more victim, older and vaster than any nation, that the failing current would wound to its core: the living ocean itself. The ocean looks the same from a boat whether the current runs strong or weak, an endless blue surface giving nothing away. Beneath that surface, the failing current would pull the living sea apart quietly, from the bottom of the food chain upward, in a way no eye on the water could catch until the nets came up empty. All ocean life leans on a hidden foundation, tiny drifting plants too small to see, blooming in their countless trillions near the sunlit surface. Every fish, every whale, every seabird traces its meals back to those tiny plants, and those plants need two things at once to thrive: light from above and food from below, nutrients lifted up from the deep by the churning of the currents. The great overturning is one of the engines that keeps stirring those nutrients up into the light. Slow the stirring, and the tiny plants starve for want of the deep's rich food. Starve the plants, and everything above them in the chain starves in turn. A weakening current would also warm and still the upper ocean in places, and a warm, calm sea layers itself like oil on water, sealing the nutrient-rich deep away from the sunlit top. The mixing that feeds the surface grinds down. Whole stretches of ocean that once teemed with life could fade toward barren, clear and beautiful and nearly empty, marine deserts where the foundation of the food web has quietly collapsed. For the fish, there is a second blow. Sea creatures live tuned to the temperature and the flow of their waters, and the current helps set both across vast regions. Change the current, and the familiar patterns scatter. Fish that gathered for centuries in reliable grounds would find their waters altered and move, or dwindle, or vanish from the places people have always caught them. The great fisheries that feed hundreds of millions and employ whole coastal economies rest on the ocean, staying roughly as it has been. A shifting current pulls that rug out from under them. Now remember what this current also carries downward, the breath of the deep sea. As it weakens, it drags less oxygen into the depths, and the lower layers of the ocean slide towards suffocation. Vast regions of the deep could grow starved of oxygen, dead zones swelling where fish and bottom life can no longer survive. The sea would be squeezed from both ends at once, its surface going barren for lack of nutrients, its depths going lifeless for lack of air. Stack it all together, and the ocean, the great blue heart of the living planet, grows quieter and emptier. Fewer of the tiny plants at the base, fewer fish in the middle, fewer whales and seabirds at the top, dead zones spreading in the dark below. A slow hollowing out of the richest, most abundant life support system the Earth has ever had, driven by the slowing of a single current, and a hungry human world, already leaning hard on the sea for its protein, would feel the emptiness in every shrinking catch. By now the scope of the threat has grown almost too large to hold. Frozen continents, failed rains, drowning coasts, dying seas, all spilling from one weakening flow. Which forces a question that has been building under this whole story, quiet and insistent. If the current is sliding toward this, why can we not simply see the collapse coming clearly enough, and in time, to stop it? The answer lies in a cruel mismatch of clocks. The problem hides in two clocks that tick at wildly different speeds, the clock of the ocean and the clock of human proof. The ocean's clock is slow and patient. This current responds to our push over decades and centuries, absorbing the warming and the meltwater with a long delayed reaction. The carbon we burn today reaches the current slowly, weakening it for lifetimes to come, the effect stretching far into the future, long after the burning is done. We are steering a ship the size of the ocean, and the wheel answers only slowly, lagging far behind our hand. The clock of human proof runs on a shorter, harder rhythm. We tend to believe a threat, truly believe it, act on it, spend and sacrifice for it, only once the evidence stands overwhelming and undeniable. We want to see the thing clearly before we pay to prevent it. That instinct serves us well for ordinary dangers, where the proof arrives with time to spare. Against this current, it is a fatal instinct because of how the two clocks line up. Here is the mismatch that should frighten us most. The clearest, most undeniable proof that the current is collapsing would be the collapse itself. The moment the evidence becomes undeniable is the moment we have already crossed the edge. And because the ocean's clock lags, the warming we have already banked, the carbon already in the sky, keeps pushing the current for decades after we finally stop. So by the time the collapse announces itself beyond all doubt, two terrible things are true at once. The tipping point already sits behind us, and the momentum already loaded into the system carries it the rest of the way down no matter what we do. This is the trap of committed change. A driver who waits until the car sails off the cliff edge to decide the danger was real has waited far too long. The time to brake was back in the fog, on the strength of a warning that still felt uncertain. With this current, the only useful action happens while honest people can still disagree about whether the threat is real. Wait for certainty, and certainty arrives hand in hand with catastrophe, holding the door open behind you as it closes. That is why the uncertainty we met earlier is such a treacherous comfort. People hear that scientists disagree on timing and decide to wait for a clearer signal before taking the threat seriously. Yet the nature of this danger guarantees that the clear signal and the point of no return arrive together, or the signal arrives second. Waiting for proof is the one strategy certain to fail. The decision has to be made blind, ahead of the evidence, or it cannot be made in time at all. Flip that grim logic over, though, and it carries a strange gift. If we must act before certainty, then the power to change the outcome sits with us right now. In exactly this foggy, uncertain moment, while the current still runs and the edge still lies ahead. The same lag that hides the collapse also means the current has yet to be fully committed to its fate. There is still slack in the line. The wheel, though slow, still answers. So the mismatch of clocks is a warning and an opening at once, which raises the last hard question. If the current did cross its edge, what would the years afterward actually look like, lived out one by one? What does a collapse feel like from inside a human life? Imagine living through it. Not as a chart or a projection, but as ordinary years passing, one after another, in a world where the current has begun to fall. At first, almost nothing announces itself. The early years feel like a run of strange weather, easy to shrug off. Winters in Europe bite a little harder and linger a little longer, and people grumble about the cold snaps and move on. The rains in distant lands come late one year, then early the next, and farmers mutter about a run of bad seasons. Nothing screams collapse. It reads as a rough patch, a spell of odd luck, the kind of thing every generation thinks it has seen before. Then the pattern refuses to break. The hard winters stop feeling like flukes and start feeling like the new shape of the world. Year after year, the cold arrives deeper and stays longer, until people slowly understand that the old mild winters are gone and will not be coming back. The late rains in the tropics stop alternating with good years and simply turn dry, season after failing season, and the word drought stops describing an event and starts describing a condition. Somewhere in this stretch, the mood shifts from complaint to fear, as a critical mass of people grasp that the climate itself has moved to a new and harsher setting. The middle years are where the systems built for the old world begin to fail in earnest. Farms that fed nations for centuries can no longer grow what they always grew, and the price and supply of food lurch and strain across whole continents. Coastal cities fight a sea that keeps climbing faster than the plans allowed, pouring money into walls and pumps while the water keeps gaining. People begin to move, first in trickles then in larger flows, away from the driest fields and the most flooded shores, and the movement of all those people strains everything it touches. The disasters stop arriving one at a time and start arriving together, feeding on one another. And through all of it runs the cruelest thread, the knowledge that it cannot be undone. Somewhere back in the early years, while the weather still felt merely strange, the current slipped past its point of no return, and no one could say exactly when. So even as the world finally throws everything it has at the problem, the current keeps sliding, carried by its own momentum, deaf to the effort. The people living through the worst of it would know that the moment to prevent it had already passed, unnoticed, years before, dressed up as an unusually cold winter. This is the true face of a slow catastrophe. A steady, grinding accumulation of harder years, each one a little worse than the last, stretching across decades, reshaping the world so gradually that there is never a clean moment to point to and say, here, this is where everything changed. The change hides inside the ordinary passage of time, which is exactly what makes it so easy to miss until it has fully arrived. Sit with that picture, and one feature stands out above all the others. The moment that decides everything is the quiet beginning, the years that feel like nothing more than strange weather, when the edge is crossed in silence, rather than the dramatic middle, when the disasters pile up and the world finally pays attention. Which lands us at last on the question that governs this entire story. Once that edge is behind us, is there truly no way back? So can it come back? If the current fell, and we later cleaned up our mess, cooled the planet, stopped the melt, would the great flow simply start again? The answer is the hardest word in this whole story, and it needs care, because it is true in one sense, and cruelly false in another. In the longest view, yes. Nothing about a collapsed current is permanent on the scale of the planet. Given enough time, the Earth's systems would grind back toward balance, the Northern Ocean would slowly regain its salt, and the sinking could one day resume. The current has switched off and on before across the deep history of the world. On the clock of the planet, collapse is only a phase, and the flow can one day return. The cruelty hides in those words, enough time. Because the time the ocean needs to rebuild the current is measured in centuries at best, and more likely in thousands of years. Once the flow settles into its collapsed, sluggish state, it sits there, stable and stubborn, for a span that dwarfs everything humans plan for. Recovery might come, yet it would come to a world so far in the future that no one now alive, no nation now standing, no language now spoken, would be there to see it. For any purpose that matters to us, for our children and their children, and 100 generations after, a collapse would simply be forever. Set that against the pace of human life and the gap is staggering. We plan in years and decades. We build for a century and call it lasting. The recovery of this current runs on a clock 100 times slower than that. A clock so vast it belongs to geology rather than history. To say the current would eventually recover is a bit like telling someone whose house has burned down that the forest will regrow in 1,000 years. True, and no comfort at all. There is a further cruelty layered on top. The collapsed state defends itself, holds itself in place, the way a ball settled in a deep second valley resists every effort to roll it home. Even if we did everything right after a collapse, cooled the planet, ended the warming, the current would stay in its broken valley, held there by its own new balance, deaf to our regret. Fixing the cause would not undo the effect. The window to keep the current runs one way only, and it closes behind us. So the honest answer to can it come back is a yes that functions as a no. Yes, on a timescale that renders the yes meaningless for anyone who will ever read these words. No, in every way that touches a human life, a human society, a human future. The collapse would end the current for all the time we will ever know. That is what irreversible truly means here. The lost lands with the full weight of forever. Because forever, on any scale a person can feel, is exactly what it would be. And this is precisely why the moment we stand in now carries such staggering importance. The choice comes down to keeping the current, or losing it for the whole length of the human story yet to come, which brings us finally out of the dark and toward the only part of this that we still hold in our hands. After all of that, here is where the story turns, because the ending is still unwritten, and the pen is in our hands. Everything dark in this tale flows from one root cause, and that root cause is something we control. The current is weakening for a simple reason. We are warming the planet, and the warming melts the ice and heats the sea and freshens the north, and all of that works against the sinking that drives the flow. Every part of that chain traces back to how much heat-trapping gas we pour into the sky. Which means the single most powerful lever over this current's future is the same lever that governs the whole climate. How fast we stop adding to the warming. Slow the warming, and we slow the melting, and we ease the pressure on the current, and we widen the distance between the flow and its edge. The current's fate and our choices are bound by the same rope. The comfort here is real and worth holding. The current is still running. Today, this year, it still hauls its warmth north, still turns the great wheel of the ocean. We are watching a warning. The wreckage remains ahead of us, and avoidable. The giant is leaning, and a lean can still be caught. Every ton of warming we prevent is a hand on that giant, steadying it, buying time, keeping the ball inside its wall. The power the mismatch of clocks seem to steal from us returns right here. Because the effects lag, the choices we make now reach decades into the future, and shape whether the edge is ever crossed at all. There is watching to be done as well, and it is already underway. The instruments strung across the Atlantic keep taking the current's pulse, year after year, building the record that will catch any deeper slide. Scientists keep refining the fuel gauge, the warning signs of lost resilience, sharpening our read on how much margin remains. The cold blob itself stays under close watch. That patch of stubborn blue now understood as the surface glow of a struggling giant. We have learned to see this danger, name it, and measure it, which is the first thing any threat requires before it can be faced. Hold the whole story in your mind one last time. A patch of ocean cooling against a warming world, a current larger than every river on Earth, quietly losing its strength, a machine that warms continents, waters billions, and breathes life into the sea, leaning slowly toward an edge that the planet has gone over before. And a narrow, precious window, open right now, in which what we choose still decides how the tale ends. The scientists who study this current handed us a warning rather than a prophecy, and a warning is a gift, because a warning means there is still time to heed it. The cold blob is that warning, written on the face of the sea in the one language the ocean has to speak. A patch of blue, growing colder, telling us that the heartbeat of the Atlantic has begun to falter, and asking, while there is still time to answer, whether we will listen. The current is still flowing, the edge is still ahead, and the story of what happens next belongs, for now, to us.